They record it. They record it. They put it in a weird place. I download it and put it back up on YouTube because it's easier for you guys to find. All right. Yeah. So it's being recorded. So all matter is made up of atoms. Atoms of an element are identical. And then basically he said compounds are formed when you take two or more elements, right? Atoms of an element, and combine them. He also said later that, so these are three things. It'll be like a multiple choice question. Gee, which of these were Dalton's three postulates? And you'll be like A, B, and C, and it wasn't a dolphin or something like that, right? So, but they'll be like these statements. Won't be exactly the same, but it'll be like these statements. But he also said when two substances react, so you're thinking about two compounds, right? What really happens during a chemical reaction is they just rearrange how the atoms are connected. And even though this was a long time ago, early 1800s, he built models of what he thought they looked like. He had these like wooden spheres that he drilled holes into, and he's trying to figure out what these formula are. And you can actually go to the Royal Society in London, and they have this cool library, and for just like a little bit of money, you pay them, and then like, I think it was like £5 or something, which is like, now it's like $5. You can actually go in and say to the librarian, oh, can I see that document from here and here and here? And he'll actually bring you out like Dalton's notes and hand them to you. It's the craziest thing. And you can actually look at the things he was drawing, like things he was thinking. And it's not just his notes, it's personal letters. So when I went there, I looked at John Dalton's stuff, of course, because I'm a chemist. And then I looked at Isaac Newton's stuff. So Isaac Newton's letters to people, and you know how they say he was a genius, and then he like wrote stuff backwards and like in different languages. Yeah, so I'm holding this piece of paper and I'm like, this is like amazing. And then who else did I see? Oh, Charles Darwin. Darwin's letters to his families about his ideas about this theory that he, like, you read these letters, you're just like, what the heck? They just handed this to me? The United States would never do that, right? For good reason. Some guy pull out a black Sharpie. Yeah, anyways. Crazy. It might have been because they knew I was a professor from the United States, because I told them that. And I'd sent them emails, said I was coming. But every time I've gone, they're like, yeah, hey, whatever you want, just tell us ahead of time, we'll pull it out for you. I'm like, this is so cool. Oh, yeah, so side note. And summer is a great time to travel to England for cheap. I could tell you like $500 a flight. It's like cheaper than flying to see my in-laws. And then I won't make any jokes because it's being recorded about in-laws.
Is that a one-way trip?
Round trip. Actually, it's like you can even do a three-leg. I'm going to do that this summer. I'm going to do a three-leg trip to Dublin, Ireland, and then I'm going to take a ferry across and go to Scotland, and then I'm going to come back down to London, and then fly out from Heathrow back to LAX. And it was just like $500. It's like, I can tell you like how to find it, but I don't know if I want to give up that information. So that's actually really easy. You probably already know how to do it, just never thought to do it. All right. And it was a fluke that I did it. No. So historical timeline. So after Dalton discovers his atomic theory, this is when people have something, remember theories have to be testable. They actually have something to test. They actually have something to do. And so Dalton does his work. One of his students named Jules, right? He's the guy who's responsible for like joules, like in your equation, right? MCAT equation. He's responsible for starting all that. And then it isn't until about early 1900s, a guy named J.J. Thomson, he discovers the electron. So now this is only, what, 120 years ago now. And before that, there wasn't like electricity or, right, the discovery of the electron. And then Rutherford is one of actually Thomson's students, and we'll talk about his experiment. His is one of the few experiments that I want you to remember, so we'll go over that in some detail. But Rutherford's the guy who figured out there was a nucleus, and he did it even though his boss, who was Thomson, didn't believe that's the way it was. He says, go over, he was, apparently, I've heard this story because I went and visited over there. I've heard this story that he was actually just trying to get Rutherford out of his hair for a while and just said, go over here and do this experiment. Because this is what I think it's going to be. Now, I don't know if that's true, but I heard it from a fairly reliable source. And then he discovers the nucleus of the atom that way. And then the last one, this is one of Rutherford's students, so you can see how all these guys are related to each other. They were all in Cambridge at one point in Cambridge, right? And it wasn't until about the early 1900s that they discovered the neutron. So the last atomic component, its nuclear component, wasn't discovered until much more recently, like within about 100 years. So your grandparents were probably alive, because he died in 74. Your grandparents were probably alive when he was alive, the guy who discovered the last atomic particle, or the big one anyways. Just kind of weird to think about. So how did Rutherford, right? How did Rutherford discover the nucleus? To start with, okay, Thomson, J.J. Thomson, the electron guy, he said, well, electrons, he discovered electrons, he knew their charges were negative. So the electrons are negative. So this is from Thomson. Let's go like that. They have negative charge. And then they also knew that all matter was electrically neutral. Okay, so all matter is electrically neutral. Like, it's not like you pick up a piece of I don't know, like a calculator and you feel a charge. So there must be, if electrons are negatively charged, and they found them in everything, okay, then there must be a positive charge as well. So he assumes that there's a positive charge. So he discovers electrons, and then he assumes positive charge. Oh, well, that's not right. Charge, there we go. Because matter is electrically neutral. And you know what it means to be neutral, right? Maybe not. I mean, that's like a term we use like in electronics and stuff. But it's when you have as many positive charges as you have negative charges. So if you have all these negative charges in substances, there must be that many positive charges. And then this is the thing. They didn't know what the atom looked like at this point. They didn't know how the positive charges were distributed and how the negative charges were distributed. And so he did know that the positive charges were big, or bigger than the negative charges. He just assumed it looked like pudding with plums in it. So that's why it's called the plum pudding model. They have chunks of positive charge floating around this big sea of negative charge, okay? So this is why they call this the plum pudding model. So that's what he was thinking. So then, you know, this is the atom. Who knows what it looks like? Actually, they didn't even know if they're really atoms. And that there were negative charges and then positive charges. And there's kind of just like evenly distributed. Didn't have any idea. Because he didn't have any other reason to think it would be otherwise. In general, we just kind of think, what's the simplest explanation? And we start with that. Okay? So what Rutherford's experiment is to do is to use something called an alpha particle. And alpha particles, and I'll put it in parentheses under here, this is really all of matter. Looks like this. Takes an alpha particle generator. And an alpha particle, oh, and that's the letter alpha. You may not know that one, but it looks like a fish swimming like over that way. So an alpha particle is a fairly massive subatomic particle. They knew it was big at the time, compared to a lot of things like the electron, because they knew the electron was small, they knew the alpha particle was going to be relatively large. So we have an alpha particle. Later it comes to find out, as they say, it's a helium nucleus. It's really, alpha particles are really just helium nuclei. And the way you generate them is you take radioactive material and it naturally produces it. And if you want to aim it, basically you don't aim it. You just contain it on all the sides except for the side you want it to go on. These alpha particles would be in this box and they would shoot out like this. All right, so think about this. He has all these radioactive materials. This is before the Curies and the discovery of like how dangerous it is and all that kind of stuff. His lab is actually in Manchester because he did a lot of this in Manchester, still closed. This guy walled it off. Like historically, this is super important, but we can't go in there. It'll be okay to go in after, I don't know, a couple hundred years, I suppose. Yeah, so alpha particle, and then he has a piece of gold foil. And again, this is called the gold foil experiment. And this gold foil is very thin, probably made this the same way a guy named Michael Faraday made it. He basically takes an electric charge and blows up a piece of gold with an electric charge and allows it to float to the surface of water. And when it floats to the surface of water, it makes a thin film of gold atoms, which he then pulls off, and you can basically see through this thin film of gold. So it's pretty thin, okay? So alpha particles, they go to the gold, and then they put up a big phosphor screen all the way around this thing. So this is like a detector. It's got a phosphor in it. And all it does is when a particle hits it, it'll glow. So they can tell when these alpha particles go through and hit, and the energy, because the alpha particles are heavy, they have a lot of energy. When they hit it, they leave enough energy to create a trace that they can see. So what do you think you expect to happen? What would you expect to happen, right? So the expectation would be that they would go through and there would be small deflections occasionally because they would get close to like a positive charge and they would deflect. Turns out alpha particles have, I should have said this earlier, have a 2+ charge on them. Okay. So they would come through and that's the unit we use now. They didn't use 2+ back then. We just call it 2+ now. It would go through and they would expect some deflection. So they expected all the deflections to be within a certain range, and they were expecting to see most of it go straight through. And this is what happened. Most of it did go straight through, but there weren't a lot of little deflections. Basically, most of it just went straight through. Right. Okay, so let me just ask you a question. Let's say I turned off the lights and I put up a big screen. And I said, the big screen may be there or might not be there. And I handed you an eraser and said, throw it to the wall. And every time you threw it to the wall, it hit the wall. What would that tell you? Spring's not there. Yeah, there's nothing there, right? Yeah, that's actually the conclusion. First observation from this experiment, all right? Main observation, most particles unaffected and go straight through. So far, so good. So it doesn't exactly conform to plum pudding model because there's nothing there, okay? So the first conclusion, matter is actually just mostly empty space. It comes directly from that idea that that's happening, okay? And here's the second kind of important observation, and there, there's more than just two, but these are the ones. These are the big takeaway. Some of them just count straight back. So most do this, and a few do this. So it's not that they're just deflected, because that's what plum pudding model would have said, because the alpha particle is fairly big. It's like if you took a semi truck and you drove it through a parking lot full of Priuses, right? Plum pudding model would have said, yeah, it's just going to go through. There'd be a little bit of deflection because you got to push some of these cars out of the way, but at 65 miles an hour, semi truck will just go through. And that's kind of the idea of the original experiment that most would go through. And it'd be like a parking lot full of Priuses and a semi truck. But here's what happens. If you saw a semi truck go into that parking lot and then all of a sudden it bounced backwards, that's the equivalent of what they saw. What would that tell you about the thing it hit? Really hard, right? And it weighed a lot. If a semi truck hits something and that thing doesn't move, it's usually called a bridge, right? It's way bigger than the semi truck. And that was the idea. Like these things were pretty large. So some particles were deflected backwards. Conclusion from that is that all the mass of matter is concentrated into a small spot. Okay? So what matter there is, besides the empty space, right, is all concentrated into a small spot. So all mass, it's concentrated into, I'm going to use more sciencey words, into a small volume. That means what? It's really dense, right? Estimations are like if you took a whole spoonful of this really dense material, a spoonful would weigh as much as the Earth. That's like how dense it is. If you could pack it all together into a nice even structure. I don't know if that's still, I mean, people used to say that years ago. I don't know if that's still true. And this is what we call the nucleus. This became the idea of there being a nucleus. And the nucleus contains most of the mass of an atom. Very small percentage, less than 1% of the mass of an atom is outside of the nucleus. It's all inside the nucleus. So that, now what's in the nucleus? Long story short, look at all the history stuff. There's two subatomic particles in the nucleus. There's a proton, and then there's a neutron. And a proton has positive charge. And we say it's got a positive charge, a +1, and we take the electron as having a negative charge as -1. So the electron has a negative charge, right? And then the neutron has no charge, yeah, because it's neutral. That's where the name comes from. Yeah, let's joke about that, but I'll skip it for now. And then, let's see what else is there. Protons, neutrons, yeah, mass. Okay, so a proton in kilograms weighs like this, around 10 to the minus 27 kilograms. Nobody wants to write that like over and over and over again. So they define something called an atomic mass unit, okay? And a proton weighs about one, even though it weighs around 10 to the minus 27 kilograms. We just say a proton is 1 atomic mass unit. Okay, so its mass on a scale is 1 AMU, and the neutron's mass is 1 AMU. And it turns out an electron, like ballparking it, is around 1/1800 AMUs. Okay, so it weighs, you don't need to know that 1/1800, but it's a nice round number. It comes up pretty close to what it is. Yeah, if you have an atom and it's got protons, neutrons, and electrons, the electrons are only 1/1800 the mass of the protons. Right, so there's almost no mass that is the electrons. Now, real quickly, just side note, and then we're going to do some periodic table stuff. Something called Coulomb's law, right? If matter is mostly empty space, why can't you just like go like this really hard and just have your head pass through the table? Right? Everything, because I just told you guys, most of you didn't really blink an eye. Most of matter, there's nothing there. You could take all the matter that's in this room, and if you got rid of all the space that was in it, it would be in a pinhead. Like you're looking at it, it's like, feels pretty solid. I'm not going to try that head through the wall thing that Dr. K said should work, right? Because you're smarter than that, hopefully. Maybe not. I don't know. We'll find out later. Come back. Someone come back with Band-Aids on their head. It didn't work. Okay. Yeah. So there's a thing called Coulomb's law. Oppositely charged. So I'm not going to explain all of Coulomb's law to you. But basically, Coulomb's law is the law of all opposites attract, right? And like charges repel. So what we have in matter, and your book draws this little picture I didn't really like, so I didn't use it. That you have positive charges, right, in an atom, and negative charges, and those are associated with each other. If you put another atom next to it, you'll have positive charges and negative charges.
What was the second thing you said? Opposites attract and
Oh, and like charges repel. So if I have a plus and a minus, right, they're going to be pulling towards each other. If I have a positive and a positive, they'll be pushing away. And if I have a negative and a negative, they push away like that. But oppositely charged objects want to be together. And so a nucleus has a positive charge because that's where the protons are. Then it has electrons that surround it because they want to be where the proton is, because opposites attract. But when you take two atoms and put them together, it turns out they want to be, they're attracted to each other because of the positives and the negatives. And we'll talk about this later. There's different ways that that happens, but these are what we call chemical bonds. And if you want to actually push your matter through something else, you have to separate those chemical bonds. Okay? So it's like a net that's held strongly together. And if you try to go through it, you got to open the net up before you go through. So that's why when you like put your hands on stuff and you're trying to push yourself up, actually what's happening is the bonds, the attractions between the positive and negatives that are in matter resist pulling apart because they're attracted to each other. Okay? And what chemists do is they figure out how to make stuff out of that attraction. Right? We try to figure that stuff out. Yeah, so empty, when it's empty space, it feels solid because of Coulomb's law. Oppositely charged objects, atoms have protons and electrons, right, are attracted to each other. You have to separate that. Okay, quick overview of the periodic table. I have a laser pointer, so I will use it. This is our periodic table in the room. It's fairly current because they have this guy here. UUP, which is funny to me always, and then UUS and UUO, right? This stands for 115, 117, and 118. So this is pentium, septium, and octium. So that's what it's, and the first part's 110. 10, basically. But yeah, they actually have this element symbol here. These are all recently discovered or created elements that are on this end. The ones with the asterisks, they haven't decided what they're going to call them yet. So at the time of this printing, they kind of knew, but they didn't know for sure. Okay. Anyways, that's what the periodic table looks like, and I'll be referring to that, but I thought I would also just print this dude out here. Just a couple of quick things. We have both groups and periods. Those are the periods. They go from left to right, okay? So a period, if you're not familiar with the word, you could also just say it's a row, okay? But you should learn the term period. And they're numbered. 1, 2, 3, 4, 5, 6, and then 7, and then we're working on 8 because, like you see, we kind of filled this up, so we're shooting for this one down here, which will be fun because it'll make everybody have to reformat their periodic tables. And then there's groups. So a group is a column going this way. Okay. So they're vertical this way, and periods are rows going this way. And then we have periods have numbers like 1 through 7, like I said, and groups also have numbers. And unfortunately, that periodic table doesn't have the group numbers that most older chemists like, the ones that make sense, okay, to chemists, is this. Okay. There's 1A, 2A, and this one says 3B, right? So there's actually 3B through 8B over here, and this one over here is 3A. So on top of boron, I have another periodic table later. But on top of boron, that's 3A. The A's in the big picture are known as the main group. And the B's are the transitional groups. And I'll explain to that again more later. And we'll on this periodic table here, right, we're going to write some of that stuff across here. Now, so that's sort of the main layout. I'm not going to go into a lot of details. I'll do that later. Okay. What I really want to do is focus on what's in those boxes. And so here's potassium. This is just a screenshot. I think it's from your book. Right. The different things that are in that box for potassium. So potassium's right here, right? It has a 19, it has a K, and it has 39.10. This one has like way more sig figs in it, 39.0983. So we'll talk about what each one of those means. The 19 is what we call the atomic number. And the atomic number it gets the symbol Z. And the atomic number is the number of protons. So when you're looking at the periodic table, it has these little numbers like 1, 2, 3, 4. People think they just put the numbers there to keep it in order. That's actually the number of protons that are in the nucleus of each of those types of atoms of the element. Okay, so there, Z, the atomic number, this is protons. K is what we refer to as the element symbol. Should have put this on the other side now that I think about it. It's the element symbol. I don't really know how much space you guys have. By the way, if you have suggestions for reformatting all this, just let me know and I'll just do it. Not while we talk, but you know, I want to make it so it's easier for you guys to use. Someday this will just replace the book, right? And you don't have to even buy the cheap book that you bought or read it. Okay, so Here's potassium. There's the name, right? But most periodic tables have the atomic number, the element symbol, and then this number. And the 39.10, which I'll write over here, is in units of AMU. And we'll give some other units to it. But that's the average atomic mass. So remember we talked about a proton weighs 1 AMU and a neutron plate weighs like 1 AMU, and electrons basically don't weigh anything, right? This is the average atomic mass for potassium. And it's in atomic mass units. And the reason it's an average is because when Dalton said all atoms of an element are the same, he was actually wrong. He was close, but atoms of an element can be different in their weight, but still their properties are basically the same. So we take the average of a bunch of atoms, just like if you want to know the average size of fish you caught, that's just the example that comes in. Right? You just weigh them all and then divide by the number of fish. You'd have big fish and little fish. Well, it turns out the number of neutrons in an atom can be different, and so you have different masses. So in nature, we just average all that together. This periodic table is it's a little bit regional, actually. Depending on where you are, those masses can be slightly different. We treat it as like one big number on the Earth, but depending on where you are, it can change. Depending on where in the universe you are, it can change. So we think that's a pretty good number, though. It's a good average number. So we'll find some of these, right? Na would be what? Here, sodium, right? What's the atomic number? 11. So it has how many protons? How many electrons for the atom? If it's neutral, it has to have 11, right? So when we get this number of 11 protons, the atom has 11 electrons. And I'm just going to call that E's and P's because it's a lot easier. Okay. And then nickel, where's nickel? And how many protons does it have? 28. It's right in the middle of the periodic table. These are one of the transitional elements. So this is 28 protons and then 28 electrons. And phosphorus, that's P. Yeah, it's right here, 15. All right, and if you wanted to, you play this game. It's on the third period in group 15, which would be 5A. Okay. You also have the periodic table that's below here, but I have to have something to point out easy, so that's just easy for me. And then so phosphorus is 15 protons, 15 electrons, and talantinum is, I don't even know where it is. Where is that?
73.
Oh, you're quick.
Huh?
You're quick.
Oh, no, I looked already.
Cheater. Did you Google it? What? Sorry. That's everybody's answer. Sometimes it's faster just to look, huh? So it's got where do you go again? 73, right? And 73 electrons. All right, so let's put some things on this periodic table because I do want you to know the groups by their old-fashioned names. And actually on this next page, you're going to see, don't fill in too much, we're going to find all these things on there, okay? But yeah, just they weren't on the same page and I don't want them. So this first one would be 1A. And the second one would be 2A. Now, old guys use Roman numerals. You don't have to. In fact, I'll try not to because Well, unless you're Roman, I guess. Seems a little weird. Then I'm going to show you where 3A is. 3A is over here. And there's a lot of really cool shortcuts you can use when you know those numbers. So 3A, 4A, 5A, 6A, 7A, and 8A. Okay? Now, then the B's go like this. This is 3B, 4B, 5B, 6B, so you get the idea, right? But here's the thing is all these, if I remember right, are 8B and then 9B and 10B. Wait, no, sorry. 8B. Nah, I screwed something up here. 3B, 4. Oh, yeah. 1B and 2B. Or not to be, whatever. 1B and 2B. So it's a little screwed up. But don't worry. For the most part, we don't talk about those guys. So we're good. And those, the B's are the transitional elements. Okay. So that's written down here. It's the last thing here. And the main group elements, if you want to put a little note to yourself, these are the A's and these are the B's. Yeah, sorry, it's on weird spots on the page. You got to do a lot of flipping. Now, the halogens, those are group 7A. So the halogens are right here on this periodic table. If you're looking on this one, right, 7A, these are the halogens. So this is the halogens down here. And if you want to, you can just like, you know, this letter that's down here, it's number 4 on the list down there if you wanted to do that. But they're the halogens that are down here. Oops. I don't know why I did that. And then the noble gases are these ones here, 8. Actually, I don't want to put that on there. I want to leave it clean. All right, yeah. So the noble gases, that's group number 3. I'm kind of going backwards from what I planned to do. Let's see real quick. Yeah. So this is noble gas. Let's see. I'll go like that. But the reason they're called noble gases is noble gases are very unreactive. Like you can, contrary to what people always say, you can make compounds out of them. It can be done, but it's hard. Okay. Basically, you have to torment them until they give up electrons, and then you can bond to them. Which makes me think like that's kind of what's happening to the royal family now, right? They're just being tormented until they give up and they left. Well, that's kind of how you have to do it, I guess. That's kind of not a good thing to say, I suppose. And then there's the alkali metals and the alkaline earth metals. So these are the alkali metals here, 1A. So that's down here. This is 1A. This is 2A. This is 8A. Oh, sorry, I'm doing Roman numerals again. This is 8A. And this is 7A. Okay. And the transitional elements are A's and B's. You know there's this little kick out in this periodic table that's here. Maybe I can I forget how you use a pointer on here. I think maybe you can't do it now. You can use the highlighter. This group that's down here, right? The way they insert is they actually insert at this asterisk. The double asterisk and the single asterisk that are there. So actually this periodic table, if it was laid out continuously, would be twice the length that it is roughly. And that group, these things here, would insert here and then split the periodic table. And these are actually just called the inner transitional elements because they're inside the transition elements. Right? And why do you think these are called the transition elements? Because it's like the transitional, actually is the word. This is a transition from the left side to the right side of the ace. It's just the stuff in between. Okay, there's not any mystery of why that is. It's just kind of what they call it. So we're going to talk a little bit about periodic law, but I don't spend a lot of time on that because I figure you guys can read a lot of the stuff that's in that section. We'll do periodic law, and then we'll take a break. And then we'll do some example problems for ions and stuff like that. Okay, so periodic law simply means this. Chemical properties repeat periodically. Trying to get this, I like how that thing just like popped up and then won't go away. All right. Maybe I have to do something. Ooh, I can open up a chat window. How about if I just get my, oh, maybe the mouse is on it? Oh, there we go. Maybe that'll do it. All right. Yeah. Chemical properties of elements repeat in a regular fashion. And the guy we attribute this to is Mendeleev. I think I spelled that wrong, but that's fine. Yeah, the guy named Mendeleev. Came up with this idea, like in the snow in Siberia, so I guess there wasn't much else to do. But yeah, chemical properties of elements repeat in a regular fashion. And then what Mendeleev did, apparently just sort of came to him. He just sat up one night and basically drew the period, because he was an expert in chemical properties. He just basically sat up one night and drew the periodic table and went back to bed. So the story goes. And what he did was he took all the elements that had, right? You're like, what? Didn't even have a cup of coffee. He took all the elements that had similar chemical properties and he lined them up like this. Now, he had some other, like he knew how much each element weighed and stuff like that, but then he realized, oh, if I just put this on top of this, then all these properties line up. So this is group 1A. When you're in group 1A, all of these things will react with water. When you watch like somebody throw a metal in a bathtub and it explodes, these are the metals responsible for that. They will all do something like that. The most reactive ones are on the bottom, so that's why they're always talking about throwing cesium in a bathtub and the bathtub explodes. You ever seen that? I'm not doing it, I'm just telling you. When I was in high school, they would take a chunk of either sodium or potassium and throw it in the swimming pool and then watch it explode. Right? Yeah, not a good idea. Well, okay, it is a good idea, but it's dangerous. It throws off bits of burning metal. I'll do it in the hood for you sometime. It's kind of fun to watch. And then we end up with, you can see splashes of silver like on the inside of the hood. And that's all metal. And then when you wipe it with a paper towel, it catches on fire. Anyways, yeah, it sounds cool, huh? Yeah. And then there's 2, right? A, group 2A. These are all have similar properties. Now, these guys all react fairly violently with water. These react very slowly with water. And then these ones over here basically don't react with water very much. You can make them react with water, but they're relatively inert. So again, we have periodic properties. They vary slowly across the periodic table, right? But everything that's in a group behaves the same. And so another name for groups that we have is we call them families. So when we talk about groups, let's see, I'll put it down here. Yeah, so he took the elements, grouped them by atomic mass, and he grouped them by their chemical properties. And they call them families because they have similar characteristics. If you saw my 6 kids, right, you'd be like, oh yeah, those all come from Dr. K because, well, they've got dark hair. And, well, actually, you might not say that because they're all taller than me now, almost, except for my daughter who's short, and my 10-year-old, 11-year-old now. But yeah, all my kids are like this. But my wife's that tall, so you can tell, like, we're a family because they kind of blended together. Kind of thing. Anyways, yeah, let's see what else is there. Now, I'll leave it at that, but you guys read that section because I'm not going to say much more about it. There's a lot more stuff in there, history and stuff. Just read that section. You'll get tested on some of it. All right, so I'm going to pause this and we'll take like a 15-minute break. Sorry, that was right out of the Peanuts. You guys know that? Oh, yeah, and I'll turn this on. Still can't believe they left the projector on all this, but anyways, they did. So, making ions from atoms. Okay, so an atom is, I'll just make this. Atoms are defined by their protons. Okay? How many protons it has, right, is the element that it is. And they're on the inside in the nucleus. They're hard to get out and they're hard to put in. So when you're making ions, right, you're only playing with the electrons. Okay, so if you have an atom and you want to make an ion out of it, you're not going to be messing around with the nucleus. You're messing around with the electrons, which are around the nucleus, okay? The other thing to remember, and this I said earlier, all atoms are electrically neutral. So we have protons equals electrons. And then we have 2 kinds of ions, okay, that we make from atoms. There's which one did I say first? Cations, and there's anions. So cat is positive. Has the T in it, right? Cation has a positive charge in it. So this is positive. I'm going to write more in there. And anions are negative. So let's say you have, I don't know, 10 protons, 10 electrons. You'll be neutral. How do you get a negative charge? No. You have to play with electrons. That's why I was saying that earlier. You have to leave the protons alone because then you're making a different element, right? So you start with your protons and electrons, and if you want to make a negative charge, you add electrons. And then to make a positive charge, you remove electrons. And to me, it's always been easier to understand charge by thinking first, I have this many protons, this many electrons. If I have a positive charge, I have to lose electrons. If I have a negative charge, I have to gain electrons, right? If you try to just do it in your head just by saying, okay, I'm going to have this charge, you're going to make a mistake. Trust me, you'll make a mistake. It seems so simple, like what I just said, like add and subtract, right? But you're always going to go the wrong way, at least once, okay? So we're going to do chlorine, right? So we want to know the charge of a chlorine atom with an extra electron, okay? So this is what we're going to do. What's its atomic number for chlorine? Where is it at?
17.
17. It's one of the halogens, okay? So I'm just going to say these words to help remind you. Number 17. So how many electrons does neutral chlorine have? 17, right? And then what did we just state it has? Has an extra electron, right? So we're going to add one. And that's going to be 18. So the atomic number is positive. The electrons are negative. So what's its charge? -1. Because it got an electron, right? That's the way we're thinking. But you have to think like it's got 18 electrons, 18 negative charges. It's got 17 positive charges. So it's going to be a -1 charge. So it's charged. And the way we write it is like that. It has 1 minus charge. I don't know. Chemists. It's just weird. If you write -1, I'm not going to be like, the nuclear bomb, 0 on your paper. I'm not going to do that. I'm just telling you, chemists will look at you like, ugh. Not me, sorry. And then, okay, so if we want to write the ion symbol for that chlorine atom, okay, then it's going to be, I'm going to just get rid of that for now. We're going to get rid of that for now. I haven't talked about it yet. The ion symbol would just be Cl-. We don't write the 1 usually. Would it help if I did that? Is that too dark?
No.
Better, right? Yeah. I noticed all of you squinting. All right, so we're going to do copper with 27 electrons. So how many protons does copper have? Where's copper? 29. Yeah, 29. So it has 29. So it has 27 electrons, right? This is your positives. This is your negatives. You have more positives than negatives, so what's the charge? +2, right? 1 for every extra charge. What that means is it lost electrons, right? It lost 2 electrons. Eventually, it'd be easy for you to think, lost 2 electrons, now it has a positive charge. But initially, people always say, lost 2 electrons, they're negative, so it must have a negative charge. And then now looking at this, you know that's not right, right? But the way we write the symbol, we would just say Cu 2+. So now we're going to do this. We're going to take some time and do this chart. Have you guys fill it in, just so you know, though, right? I left different things out of every line. So here you have the sodium, so the element name, right? You're going to have to figure out the symbol if you don't know what it is. You get the number of protons. I gave you the number of electrons it has, and then you can figure out what its charge is. Right? Here, I told you what its charge is. I gave you the number of protons, so you have to figure out the blanks. Right? So see how you do with that. And then we'll go through it. I gave you like, I don't know, 3 or 4 minutes. And then I'll walk around and point it. That's not light. Should give you guys a periodic table. I'll have some printed. Hand them out. almost done. Did you start recording? Yeah, I did. I think I did. I don't remember now.
You did.
I did? Okay. Yeah, I did. You're serving the role of my wife right now. Did I do that? Yeah, you did. Okay, good. I did it. All good. It's not old age. I've just always done that. I'll never say it very well. All right. I'll do the first 2 lines, and then we'll see where we're at. And then if you guys are getting it, I'll just let you figure out the rest on your own. All right, so sodium, right, is Na. So it might be helpful to write that symbol in there. And then it's supposed to have 11 protons, like that. So I have more positives than negatives, right? So its charge is +1. Right? Yeah, I actually would write 1+, but I can't even do it all the time. Now, the next one I didn't tell you, like, which element it is. How do you figure it out?
You look at the proton.
Yeah, you look at the protons. That's your atomic number. So it's chromium. So it's Cr. That's chromium. Like chrome plating, that's what makes the shiny on your car. Well, now it's plastic. But in the good old days, it was actually chrome metal. Okay, so that's chromium. It's supposed to have 24, right? And it has a 3+ charge. So what does that mean? Yeah, and so you have to have 21 electrons, yeah? Because you have to have fewer electrons. You can't, like what people will always do is try to change the number of protons or something. That's just a different element. You can't do that. What about the next one? 35 electrons is neutral. I made it easy. Yeah, so you got to look for 35 protons. Right? It's bromine. So it's 35. And then it's bromine. And then I'll let you figure out that last one. But I did want to write this too. The element symbol, when you write it, would be Na+ or Cr3+. Bromine would just be Br. And then strontium with 36 electrons. So it's supposed to have 38, right? You look up strontium, that's Sr. Bromine is Br. So you're going to have 38, right? And so it'll be 2+, and then that'll be Sr2+. Right. There you go. Now, we'll talk a little bit about what happens when you change the number of neutrons. And isotopes have the same number of protons. So protons are the same, but they have a different number of neutrons. And so we define something called the mass number, specifically for isotopes. We define something called the mass number, and the mass number, which is usually given the letter A, okay, is the protons plus the neutrons. And we write something called, from that, we write something called a nuclide symbol. And the nuclide symbol, that's what I kind of was doing before. But you would write, let's say, it for bromine, okay, with, let's see, 35, right, 35 protons. And let's say I'm going to make up a number. Let's see, where's bromine's mass? It's about 79. So we'll say 40. I'll just make up a number, 44 neutrons. Yeah, that'll work. Then the mass number, A, would be 35 plus 44. That'd be 79. If my math is still good. Yeah, still good. And then the nuclide symbol would be like writing Br. Okay. And then you would write 79, and you would write 35. Now the 35 could be left off because once you have the BR, you know the 35, but it's nice to just, that's what they usually do. They usually put the atomic number right there. So this is that. You need the protons, you need the mass number and the element is basically what you need to do that. So the periodic table though only gives you the atomic number, so like bromine, right, and the symbol. The mass number is actually for elements is usually measured. It's not on the periodic table anywhere, but it turns out like for bromine, right, you'll notice that its average mass, what does that say up there? Like 79, right? It's usually pretty close. The average mass is usually pretty close to the number of neutrons because that's what makes up the mass of an element. So this particular isotope of bromine has a mass of approximately 79 atomic mass units. It's not exactly that for lots of reasons, but basically it's pretty close to that because it has a sum of 79 nuclear particles, which each have a mass of 1, right? So it comes out to pretty close to that. That is not that number there. It turns out there's 2 isotopes of bromine. There's 79 and 81, and they kind of like, there's different percentages. It's not 50-50. So we're going to do some calculations to figure out how that is. Yeah, and I just did all that, sorry. So we're going to write the nuclide symbols for carbon-14. Carbon-14 is the dating isotope. Like when archaeologists say, or anthropologists say, oh, this bone is like 35,000 years old. You're like, how do they know that, right? They did it from radioactive decay of carbon-14. So carbon-14, right, you're going to be C, and you're going to put 14 up here, and then you can write a 6 here. If you wanted to know the protons, well, you just look at the nucleide symbol 6, right? And if you wanted the neutrons, you just subtract, and it'll give you 8. That's how I've always done it, but you could also just do the math. You say A is equal to P plus N, and if you want to know the neutrons, and N is equal to A minus P. But really what that is that. So if you just line it up and subtract, that'll be the number of neutrons, right? The neutrons in carbon-14 is equal to 8. Most carbon only has 6. Most carbon atoms have 6 protons, 6 neutrons. Their mass is about 12. And actually what we do is we look at the ratios of carbon-12 and carbon-14, and that's how we establish how old an object is. Carbon-14 is radioactive, which means it slowly decays away over time. So if you have an atom with 12 protons and 13 neutrons, right? What's its element symbol? I'll look at the periodic table. Magnesium, Mg. Right? And then that's the 12 that's down here. If you take 12 plus 13, that's 25. That'll be its mass number. Like that. Still, in all of these cases, unless it has a charge on it, unless it's an ion, protons and electrons are the same. Again, there's a couple of different flavors of magnesium, mass, isotopes. But let's see, the one that has the most isotopes, I think, is tin, which is way down. Tin is SN. Like it's Latin is stannous. So like, stannous fluoride, you brush your teeth. That's that stuff. I think it has like 10 different isotopes. So in nature, its nucleus is oddly stable with all kinds of different number of neutrons. And so there's like 10 different isotopes for that. Okay. And that's another weird reason I'm not going to go into. But if you want to know, take Chem 1B, and that's the very end of the second semester of general chemistry. You'll get to why tin is so stable. Okay. So fill this table out. See what we get. Give you like 2 minutes. impatient. I'm like, is that 2 minutes yet? Dan having stuff in front, but when I'm lecturing. Okay, that's better. Oh. We'll put a periodic table there. Dang it. I'll just draw it. I'm just start writing. Copper is 29. So I filled in most of it, except for the last bit. Right? I just got the atomic numbers. I got these, right, from the periodic table. Just filled them in. And then I set it up like this to subtract them. And then when you subtract them, you'll get the number of neutrons. So for chlorine, it's 20. And then for copper, it's 36. Yeah, it's 36, yeah. And then I left space down here if you wanted to write more notes, like how it was done. I just left just some space. Now, if you have isotopes that are cations and anions, it's the same thing. So like if you had a copper, another way to write it is 65, right, with 27 electrons. You would write Cu, and then on the left, you'd put 65, and on the right, you would write 2+, like that. So you just pile all these things on. So if you have an isotope that has a charge, you just do it exactly the same way that you've done before. You're just adding the isotope, the mass number to it. And then the copper, like I said, you can either have this down here or not because they mean the same thing. So either way is acceptable. I'll write both, actually. And like on a test, right, I'll tell you, oh, which isotope symbol is correct, and you would just have to pick the one that matches one of these.
Is that 27 or 2+?
2+. That would be a trick. Yeah, this is 27 here, and that makes it 2+ here, right? Yeah. And then for anions, it's the same thing. So let's say it was bromine, 81 with let's say 36 electrons. Then it would just be Br. You would still write the 81, just like it was an isotope, because this is an isotope, and then you would put the charge, just like you normally would. And that would be -1, because bromine's supposed to have 35 protons and electrons. It's got 36, so it's an extra electron, so a minus charge. Okay, so that's a very important idea here. And then we'll explain why it is a little bit. But for the most part, you don't really learn why it is until like chapter 9. So one of the things that you can get from the periodic table is the common ion charges. So there's some elements, and I'll show you which ones, produce only one kind of ion, typically. One type, cation, anion, and charge of ion. This is supposed to be, you know, type is cation, anion. I'll write that. So for example, right, sodium is always +1. Magnesium is always +2. And I'm going to show you how you figure that out from the periodic table, because I don't want you to remember like them all separately. The periodic table is arranged according to periodic chemical properties, and the ion charges is one of them. Okay, so I'm going to draw a periodic table because I didn't put one here. That's okay. We'll figure it out. Whoop, whoop, whoop. Got to make that sound too. Wait for it. I think I screwed that up somehow. How do I want to do that? I got to go straight across from there, huh? Yeah. Yeah, over here, there's helium over here like this, right? Yeah, it's a little distorted. Where's my periodic table? All right, so this is 1A. This is 2A. And this is 3A. This is 3B. Okay, so go like that. And then this is 8A, 7A, 7A, row 78, 7A, 6A. So I'm not drawing the whole periodic table because you can't do this with the whole periodic table, right? So if you're in group 1A, your ion charge is +1. Like always. So like what, if you get the question, rubidium's charge as an ion, there's only one answer, and the answer is it's 1. And you can get that from its group, right? So like these are all +1. Hydrogen can actually make a -1, but as a cation, it always is +1. What do you think group 2 is going to be? 2. Yeah. This will be +2. Now, group 3B, okay? Group 3B is right here. And really, these are the 2 elements that we're concerned about. Now, your book doesn't include this one, but it does include this one. If you're talking about ions that are common, like if you were like pull it out of the ground kind of common, these would be, what do you think? Charge plus. Now you know how Mendeleev could wake up in the middle of the night and go, hey, this is what it is. Yeah, so these are 3+. Okay. And really people usually just include scandium, but yttrium is also one of those. And then there's 3 more of the metals. Okay, now I forgot to define the metals for you. I'm going to scroll back to here. I forgot to do these 2. And on this periodic table, right, aluminum is a metal. I'm going to draw stairs like this. And then the non-metals are everything to the right of this. Let's see, antimony, bismuth is a metal, polonium. I think this is also one of those, yeah, like that. So non-metals are here. Non-metals are on this side. The metals are on this side. So if you're looking at that, which are there more of? Yeah, way more metals. It's a lot of metals. Most of the periodic table is metals. That stair step that I drew along here, everything to the left of that and everything at the bottom, those are metals. The only things that we have that aren't metals are on the top right. Now you need to know the properties of metals and the properties of non-metals, but that's just like a list, like metals are shiny, metals conduct electricity, metals conduct heat well. That's in your book in that section I told you to look at, so you go look at that section. But know the properties of metals and non-metals. And then the guys inside the stair step, like boron, silicon, germanium, arsenic, antimony, tellurium. I think polonium is actually a metal. That line should have quite gone down so far. Those are all called the semi-metals. So if you think about periodic properties changing as you go across the table, if you have a lot of metals on the left side and a lot of non-metals on the right side, somewhere in between there has to be a transition between metal and non-metal. And that's this stair step that I've drawn right here. Okay. Now you can look in your book, they define it a little bit more carefully. I'm not that concerned about it, but you need to know that they exist. And I might ask you like silicon and germanium, because like the Silicon Valley and semiconductors, right? They don't conduct electricity as well. That's one you should know. Okay. Germanium is also used in the semiconductor industry. Semiconductors are the semi-metals. Okay, now having said that, there are 3 more metals that you need to know the charges of. Actually, I guess it's maybe more than 3. It's 1, 2, 3, 4. I'll say 5, 6. And they're these: aluminum, and then zinc, and then silver, and then underneath zinc is cadmium. And then books don't usually include these, but it's usually true, so I like to include them because they make a nice little triangle in the periodic table, right? What group is zinc in? Remember, we drew that on that periodic table we just went back to. What group is zinc in?
2B.
2B, all right? And we also said it's also 12. That's the new way to do it. So there's a 2 there. The charge of zinc and cadmium, what do you think it is? It's positive, right? But it's in group 2B. Why on earth would they put a 2 on top? Because that's its charge, okay? So the charge of zinc, if you just take 12 minus 10, or the charge of silver, 11 minus 10, that's the charge of those metal ions. So these are +1, or I should say 2+, sorry. 2+, sorry, 1+, 2+. And what do you think silver is going to be? What group is it in? You know, you're looking at it.
1B.
Silver?
Yeah.
AG?
Yeah.
Oh, sorry, yeah, sorry. Aluminum. Aluminum. What's aluminum?
3A.
3A. So what is aluminum's charge going to be? 3, yeah. So the thing about common ions, the metals make cations. And you can predict their charge based on the periodic table. Now the nonmetals, if you look at your periodic table, there's only nitrogen, oxygen, fluorine, sulfur, phosphorus, chlorine, selenium, bromine, and iodine. Those are all the nonmetals that aren't noble gases. And then the noble gases are all nonmetals, or all gases, right? Those are all the nonmetals. This is how you do their charge. If you're 7A, all right, that's the halogens. These are all -1. 6A is -2, and 5A is -3. So basically, when you're looking at this periodic table, right, this is, if you're thinking about where this is 0 over here, you're -1, -2, -3, and what do you think carbon will be? -4. It doesn't come as like an ion by itself very often, but when it does, it's 4-. That's what the miners use to light the helmets up with a carbide. It's a 4- ion of carbon. It's very reactive. And it makes a combustible gas. Yeah, so those are the common ions on the periodic table. The nonmetals you get by just counting from the right, -1, -2, -3. And then if you think about it, from here, you're just going 1, 2, and 3, going positive. You're starting at the noble gases being 0, because if you think about where these elements are, they're actually to this side. by atomic number. And this is 1, 2, and 3, and this is -1, -2, -3, -4. Okay? So metals make cations, nonmetals make anions. All right. Yeah. So this is going to be some math and some terminology that goes along with it. It's not hard, but we have to kind of go through it. I'll show you. We have something, we're going to talk about atomic mass, okay? An atomic mass is measured in atomic mass units. And there's two ideas I want you to have before we get started. There's the mass of an isotope, okay? So an isotope has like a specific number of neutrons in it, right? And a specific number of protons in it. So the mass of the isotope is for one atom, and it's for a specific number of protons and neutrons. And then there's the mass of an element. And this is actually what's on the periodic table. So we're talking about mass of an isotope, we're talking about one particular atom with a certain number of protons and neutrons, and we weigh it. Now, how we weigh it is a thing called a mass spectrometer, which I'm not going to go into. I used to go into it. It's like, it's not that interesting to you guys. If you want to read about it, it's great. If you want me to explain it to you after class, great. I love talking about it. It's good stuff. But we don't have time for it. And then there's the mass of the element, right? And the mass of the element is an average. So it's an average mass of the isotopes, right, depending on their abundance. So what do I mean by abundance? Right, we'll define that next. The abundance is the percent available in nature. I just abbreviated, sorry, I didn't want to write all the way. And the mass is what we've referred to as the isotopic mass or the exact mass. That's again, the mass of an element. Those are the two things that the average depends on, right? So like if you go fishing and you catch a whole bunch of bluegills and one bass, you don't weigh the bass and say, well, that was the average weight. I mean, you might, it's fishing. You don't usually do that. You would weigh them all, right? And then you divide by the number of fish. And of course, the average mass would be really low, but if you caught all big bass, if you caught 1 or 2 sunfish, you'd probably average that together, right? Same way, you add together and you divide by the number of fish you caught. So the number of each type of isotope will change what the average mass is. So this is some example data. This is for lithium, right? There's 2 isotopes that are stable. So when we're talking about, right, available in nature, we're talking about the stable isotopes. A lot of isotopes aren't stable and they decay away, and over the time frame of the universe, they don't exist anymore. But at one point when you guys know where like the elements come from? Have you ever heard this story? Like, we're not the first thing in this neighborhood. So there was, before we existed, there were other stars that supernovaed, and when they supernova, that's where all the heavier elements come from. And then it reaccretes and forms new stars and planets with all the heavier elements. So we're like literally, we're not the first house here. There's actually was a house before that they leveled and they just built more. Okay, takes some time. It's not like, oh yeah, let's go. It's not like you can demolish your house and build on it in a year. You can't do that. Okay. So here's some examples though. So this is lithium, right? 6 and lithium-7. Their exact mass, their isotopic mass, is close to 6 and 7, right? Because 6 is the mass number, and that's the protons and the neutrons. And so this number is pretty close to this number here. But this is the percentages. So if you look at these two and you say, oh, it's 92% lithium-7, which number is it going to be closer to? Like the average is going to be closer to for the mass. If I average the masses together, is it going to be 6.5? No, because you have a lot more of this, right? You have 90% of this. You have 9 times more of this than this. Actually, about 10 times more. Right. So how do you figure out what the average weight is when you're just given percentages? And kind of the simple answer is assume the percent is the number that you have. So I have 7, you can't have 5.59 atoms, but let's just say you had 7.59 atoms. And each one of them weighed 6.015 grams. How would you figure out what the total weight is? Just multiply them together. So this is how many you have. So assume you have 100, right? And you multiply these two together. This will be the total weight. So now I need my calculator. This is the whole reason why I pulled this out earlier. I'm going to take 7.59, and I'm going to multiply it by 6.015. And I'm going to get 45.65385. A lot of numbers, only 3 6 picks. 45.65385. And then I have 92.41, right? Lithium, which has a mass of 7.016. If I multiply that together out of the 100, that's how much that weighs. So I'm going to take 7.016 times 92.41, and that's 648. .34. I'm going to say 9. I'm going to round. I don't want to keep writing all those digits. Now, there are 3 sig figs in this number, and there are 4 in both of these. So this one is good to here, and this one is good to here. Because that would be, when you multiply, right, keep the least number, and then I'm going to add them together. So that means I can add them together, and I can keep everything to the left of that line, because that's the last place I know it, but I'm going to use the unrounded numbers. So I'm going to add 648 blah, 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 to 45.6 blah, blah, blah. Like it's 694. .002, and then it goes on. I really only needed this number here because that's for the rounding purposes. Now, how much, that's the weight of how many atoms though? That's the weight of 100, right? So if you want the average, you just divide by 100. Because I assumed I had 100, and I assumed that 7.59 of them had that mass, and 92.41 of them had that mass. And so you multiply those together, I'll get a total weight, but that's for 100 atoms, so then I just divide by 100. Take that, divide that by 100. Oh, and I should point out, these are all in atomic mass units. So this is going to be 6.940 AMU. And from the periodic table, it's 6.941. It's just slightly different. So that's your average atomic mass. And you can see it like in the numbers, right? This is a calculation of the average atomic mass. All right, it's closest to lithium-7, which is 7, and this is 6.9, right? Simply because it's a bigger percentage of the total. Whichever isotope is the highest percent abundance in nature is the one that the average comes out closest to. Now, take a look at this data. And I'm going to have you guys do this one and calculate the average atomic mass. And this takes a while to do, so while you're doing it, I'll be doing it. Which isotope is this going to be closest to? Right, it's going to be closest to the 24, simply because it's about 80% of the total. So go ahead and calculate the average atomic mass. I'm going to do it up here while you guys are doing it on your paper, and then you can look up periodically and see how you're doing, okay? And track sig figs. Some of you on those sig fig problems in the homework just did the math and didn't do the sig figs. Do sig figs all the time. I get why you did it that way, but this is not a math class. It's a science class. Well, I shouldn't have done that one. That's 249. I broke the pen of this pen's tip. It's all squishy now. Makes it hard to write. And then oops. That's actually the last thing for today. And then we're going to talk a little bit about lab. So when you get done, you look up and see if you got 24.31, right? And what did we say? It would be pretty close to the 23.985 because that makes up most of the mass. And so 24.31 is a little bit bigger than that mass because the other isotopes are heavier than that. But again, it's 80% of it, so it should be pretty close to that. So the process, right, to calculate the average atomic mass, multiply, right, mass times percent to add results atoms of the isotope. Add all the masses together. Divide by 100. And then lastly, check sig figs. And if it's an element off the periodic table, like look to see if you're close to the elements on the periodic table. If I ask you this question on a test, right, I don't want you to write the number from the periodic table. One, I'm going to change it so it's a little different. And two, I really just want to see that you know how to calculate an average mass. So you'll show your work. If it's a written question, you show your work. If it's a multiple choice question, I'll certainly change it so it's not the number up there, but that number will be one of the answers. But it won't be the one that you calculate. Okay, last thing I want to do you have questions? Follow that, right? It's a pretty straightforward process. Think it through, though. It's a very important idea just to be able to use percentages to calculate an average weight. It's known as a weighted average, is what it comes out to be. And this last 2 pages are just notes that I didn't delete, so I accidentally printed them out. So I'll try to get those posted, like we did chapters 1 through 4. I'll try to get those posted just as a reminder. This Friday is the last day to drop without a W. Like, I don't want you guys to drop. I'm just telling you if you feel like you're overwhelmed. It was like the one person who hadn't had like math in like 10 years and hadn't had any science classes. Yeah. I think she probably didn't add is what she ended up doing. But yeah, this is the last week to do that. And then after that, you have to take at least a W. I think that's this week. So very quickly, we'll go over the lab for next week. And I'm just going to go over here and go to modules. So this week's lab, the next experiment is properties and changes of matter. So you're going to be dealing just a couple of things to make note of. I'm just going to write it up here, okay? You have to have a lab coat of goggles. Or safety glasses. Now the safety glasses, I don't think I've seen any here that are acceptable. The ones that look like glasses are not actually acceptable. Like this kind, I don't really allow these. Because unless your forehead is shaped exactly like that, which I hope it isn't, right? And you put these babies on, right? What's going to happen is when it spills, it'll just run down your eyes. The type that does work, yeah, I don't see any in here. They're called visor dogs. I think they have some in the bookstore. It's actually just like a visor with no sides, like not solid sides, and it pulls against your forehead. And then it comes down around the side so you can't get splashed from the side. Those are acceptable, okay? So I'm going to write that. Yeah, safety glasses, I'm going to put a line through it, but visor dog, those are fine. So these you have to have this week because what you're going to be doing is you're going to be mixing a bunch of chemicals together. We'll talk a little bit about, I want to talk a little bit about science of chemical reactions so you're kind of pre-ready to go when we get here. Oof. Yeah, let's do this. All right. Zoom is not very good. So you're going to be dealing with like chloroform, which you don't want to get all over yourself, right? And water, which is fine, and xylene, which you really don't want to get on yourself. We have gloves, so you can wear that. They smell a little bit bad, but you just really want to be wearing eye protection, and you want to have stuff on your body to protect your clothes. And the other thing that you're going to be doing, and you're going to be trying to figure out which is more dense, and you'll just be taking 2 liquids and mixing them. The way we're going to do the lab, because we do the, I didn't plan on this, but the way we are doing the lab, because we're doing exactly the same time as another class, we're going to have less stuff. I'm going to set up that first experiment. It's all going to be right here. And then half of you will start here. And the second experiment will be on the back bench. So you guys are going to clear all your stuff off when we do lab. Okay. And we're just going to come and do lab because I finished lecture for the week. And then when you're done, you'll do the post lab and stuff. But then when you're doing the experiment, you do the second half. So half of you will start on part 2 and half of you start on part 1. And when you're done, you'll just rotate over. I'm not going to control when you rotate over, but I'm just going to rotate over. Now, part 2 does take a little bit more time because they talk about all these solutions here in the experiment. These are all solutions unless it says solid, but I think it's all solutions. And what you're going to end up doing is you're going to end up making the solutions. So a lot of them, you're going to have little solids like this. And they're numbered to try to keep them together. But this is the sodium sulfate anhydrous. The sodium sulfate anhydrous, is it up there? Sodium sulfate's right here. You actually don't mix the solids together. You make a solution first in a test tube, and then you mix those together, okay? If you need droppers, usually we leave them out of the drawer, but you're gonna need droppers. They're back there behind that guy in that white box. I don't know if I can hit it with the pointer right there. Yeah, that's the, and those are disposable. So you use them for a set of experiments and then you pitch them, okay? It's just cheap polyethylene soft droppers. Now, things for chemical reactions, right? Signs for a chemical reaction are these. Color change. So you'll see that in this experiment. There's also heat. Now, how do you know when it's hot? You feel it, right? So you're gonna have to hold these little test tubes in your fingers, and you're gonna put the stuff in it. You'll swirl it around. Now, the recommended way of doing that is you're gonna have, of course, test tubes, which are really dirty, but they can be washed out. And then you just put the two together, and then you can stick this there and spin it. And then you'll mix it real fast, and that'll make the reaction go fast. Now, some of them you're going to do that, and stuff will start foaming out the top. Okay, there's gloves right there. It won't kill you, but it's like, I think, hydrochloric acid and some other things that are not good for you. So, goggles. Okay. So, color change, heat change. This would be temperature change. Sometimes things will get cold. Any other signs you can think of a chemical reaction? Like you've done experiments as a child? No, we did experiments. You did experiments. Bubbles, yeah, you see gas form. That's one of the favorites. My son, I came home the other day and he's got a mason jar with a Post-it note on top. It says, I'm doing a thing. I'm doing an experiment. It's full of lemon juice. He's got an egg in there. And he's got one with vinegar and an egg. He's trying to dissolve the shell, but he wants to know if the lemon juice will work because he learned about acids in foods. He's trying to dissolve them. Okay, good. They managed to break them in the backyard this way. Yeah, so he's doing a thing, an experiment. Right, so color change, heat, gas. Very common one is solid forms from solutions. So when we talk about a solution, we're talking about something that's homogeneous, that like is clear. Maybe has color to it, but it's clear. And the solid forms, and that just looks cloudy. Anytime you see cloudy, that's a precipitate. Let's see, heat. Oh yeah, and the last one, you don't see this one very often. Oh, if you manage to make it through like all the chemistries and end up in my organic chemistry like 2 years from now, we'll make luminol, which glows in the dark when you put blood in it. It's really cool. Yeah, but see, light. That's luminol is the same stuff like the criminologists use to find blood splatters. So we make it in lab and then we make solutions out of it. We bleed ourselves into it. It's a lot of fun. Now for the pre-lab, super simple. You got to classify chemical, physical changes and properties, all right? And then you got to classify as an element, as molecules. Ionic compounds contain metals and nonmetals. We haven't talked about those yet. So that last question is a little head, but ionic compounds, metals and nonmetals. Homogeneous means clear, right? And heterogeneous means like not uniform. We talked about that a little bit. Things that are heterogeneous, homogeneous. Okay, so those are the definitions, but we haven't talked about ionic compounds. Molecules is all nonmetals. So things that are all nonmetals that are written as formulas, basically, those are molecules. Okay, so those are the two things I didn't really talk about in there yet, but we will get to those eventually. All right, so any questions? All right, so you do the pre-lab now if you want and take off. I'll leave it up for you to write it on paper. And then otherwise, you're allowed to leave. What time was it supposed to be? 10:50. Whew, I got to get better at using the timer. All right, so stop recording.